In this video, we're going to be looking at topic 1I, electrolysis, and this is the last part of Unit 1 for the triple chemistry content as part of the IGCSE course from Edexcel. So we're going to be linking what we already know about covalent and ionic compounds in terms of their electricity, and this will link back to your bonding topics. We're then going to be focusing on the ionic substances and referring to the correct terms in terms of anion, cation, electrolysis, electrodes, and learning the key information, and then focusing on the electrolysis of molten compounds as well as aqueous compounds and how we can predict what we will make, and also how to write out ionic half equations and why we link these to oxidation or reduction. So this will also link in to topic 2D, the reactivity series. So you may wish to watch that video first before you have a look at this one, but you don't necessarily have to know about the reactivity series in order to do this topic. They do link in together, and they do help each other. So firstly, what do we mean by conducting electricity? Well, in order for something to conduct electricity, there has to be some form of charged particle that is free to move. The charged particles can either be electrons or they can be ions. And you should be able to determine if a substance will conduct electricity based on its bonding. You have done that previously when you have looked at covalent, ionic, and metallic bonding. So as a summary, for metallic bonding, we know that these are positive ions surrounded by our delocalized electrons. So these can conduct in all states of matter because they have these delocalized electrons that can move. For ionic bonding, our solid ionic substances will not conduct as the ions are fixed in place, or they cannot move because they're in that lattice structure. Whereas for molten or aqueous, the lattice breaks and the ions can move, so these do conduct. When it comes to covalent bonding, they do not conduct in any state of matter because the electrons are held so tightly in these covalent bonds and they cannot move. The one exception here, however, is graphite. And we take advantage of the fact that graphite can conduct electricity but is very unreactive when we carry out electrolysis. This is something that's very useful to us. So our main focus is going to be here, ionic bonding, and particularly molten or aqueous. This is the whole point in this electrolysis topic. So some key terms that we have to know. So electrolysis is a chemical change that is caused by passing an electric current through a molten or aqueous compound. Now, what is that chemical change? Well, it is the breakdown or the decomposition of the compound using electricity. That's how the word actually itself breaks down. We have electro, which stands for our electricity, and then we have lysis, which means to split. So we have splitting or the breakdown or the decomposition of an ionic compound using an electric current. And these have to be either molten or aqueous. And these are the ones that we'll focus on as we go forward. We then use the term electrolyte, which is the liquid or the solution that undergoes the electrolysis. So this is your molten or your aqueous ionic compound. That's what we call the electrolyte. And the electricity is passed in and out of the electrolyte using electrodes. And these are just graphite rods, which are unreactive, but they can conduct electricity. That's the most important part. They have to be able to conduct, but we don't want them to react with the substance that's undergoing the electrolysis. We solely want this decomposition to be because of the electricity, not because of anything else. So typically they are graphite. Sometimes you can get platinum rods as well. So as we said, the carbon in the form of graphite are typically used for your electrodes because they are inert. And now we have to name our two electrodes. We have a positive electrode, which is known as the anode, and we have a negative electrode, which is known as the cathode. And these electrodes are hooked up to a battery or a cell, and that's why they are either positive or negative. And to help you remember this, the mnemonic that we use is don't panic. Positive is anode, negative is cathode. PANIC. And that helps you remember. So this is one mnemonic that is very important for you to learn. Because as we move forward, we're going to be using the terms cathode and anode rather than positive electrodes and negative electrodes. So this is how we set up our electrolysis apparatus, and we've got two different parts here just depending on what we want to focus on. So if we focus on firstly what the electrodes themselves look like. So we're attached to a battery, one electrode being attached to the positive side, one being to the negative side, and this is what then determines which electrode is which. So when it's attached to the positive, then this is your anode, and when it's the negative, this is your cathode. And one thing that we need to understand is that within our ionic substances, we are going to have our cations, or our positively charged, and we have our anions, our negatively charged ions. And these are then going to be attracted to one of the electrodes. And the most important thing that we remember is that opposites attract. So when we take this setup with our electrodes in our battery and we actually put it into a solution, our electrolyte solution is going to be made up of our cations and our anions, and we can see that here. And when we put the electrodes in and we turn the power source on, we start to see the anions, which are our negatively charged particles, being attracted to the anode, and they will undergo some sort of reaction there, which we'll talk about later. And the cations, our positively charged ions, are going to be attracted to the cathode because the cathode is negatively charged. So that's the most important thing. We have our opposites attracting to pull these substances together. Now, when we're looking at electrolysis, there are two different types that we have to focus on. The first one is the electrolysis of molten compounds. So this is when we've taken the ionic substances and we melt it. So the apparatus that we use is we've got a crucible that contains our molten substance that we've then obviously had to heat, and this is known as our electrolyte. In this case, we're using lead bromide, or PbBr2. We have our carbon electrodes connected to a bulb and then connected to a power supply. The reason that the bulb is there is the bulb will light, and that shows us that electricity is starting to flow. If the bulb is not lit, then the electricity is not flowing and the electrolysis will not be happening. So we just use the bulb as a way to make sure that this reaction is actually taking place. And then when we leave it to react, what we start to see is we start to see bubbles around the positive anode, and then we see a gas being given off, and around the cathode, we start to see molten lead being formed at the bottom. So we are forming bromine gas and molten lead. So to summarize this in terms of the overall reaction, we leave our bulb unlit until the lead bromide melts. Once it lights, then we have our electrons flowing and the electricity is passing through the wires, and we are getting this reaction happening. As we leave it, then we start to see the bubbling and that brown gas being formed at the anode, and then the molten lead forming underneath the cathode. And when the heat stops, the lead bromide solidifies again, the bulb goes out, and the reaction then stops. But what we have to be able to do is to go into more detail and say what is actually happening at the cathode and what is actually happening at the anode, and we can even use equations to help us with this. So we're going to start off by looking at the cathode. So we've got PbBr2, and this is going to form a lead 2 positive ion and 2 bromide 1 negative ions. So for every PbBr2, we're going to make 1 lead ion and 2 bromide ions. So at the cathode, the first thing that happens is, of course, your power goes on. And as the power goes on, we get electrons being pumped towards the cathode from the battery, and that then makes it negative. Okay, so the electrons here, we have to be very aware that the electrons are not in the molten substance. The electrons are in the wires and the electrodes. Okay, so the electrons are never in the molten substance. They exist only in the wires and on the electrons, and in the electrodes, sorry. So as the power is turned on and we get this negative charge being built up within our cathode, that then, so then forming the negative cathode, that then attracts the positive lead ions. So these are 2+ ions, so because they are positive, they're going to be attracted to that negative cathode. When they get to the cathode, they pick up 2 electrons from the cathode to form neutral lead atoms. So the electrons move from the electrode off into the lead ions, and they then form this neutral lead atom. And those lead atoms then collect at the bottom underneath the cathode to form that molten substance that we see. And we can write this using what we call an ionic half equation. And the reason that we call it a half equation is it is only half of the overall reaction that is happening. This is only what's happening at the cathode. We then have a half equation at the anode, and we combine the two together to give us the full equation. So what's actually happening? Well, we have a Pb2 plus adding 2 electrons to make Pb atoms. That is the half equation. So the lead is gaining 2 electrons to become molten neutral lead atoms. So this is what's happening at the cathode during this process. If we switch it over now to the anode, this is happening at the same time as what's happening at the cathode. So what happens here is our electrons, when we're turning on our power, our electrons are moving away from the anode because we've said they're being pumped towards the cathode, and that's along the wires. So when that happens, we then get a positive anode because it's losing all of those electrons. They're going towards the cathode, and that then attracts the negative bromide ions. Okay, and we need to make sure that we understand that this is bromide for the ion, not bromine. Bromine is the atom and the molecule. Bromide is the ion. So our positive anode attracts those bromide ions. The bromides lose an electron because they're negatively charged. They have an extra electron, and they lose that to become bromine atoms. So that electron is then going now from the ion into the electrode, which can then go along the wires back to the cathode. And we're forming these bromine atoms. And then we get 2 bromine atoms joining together to make Br2, because remember, bromine is diatomic, so we want to make Br2. And again, we can write a half equation for this. So we have got a Br minus, and we're going to be forming bromine atoms, but in reality, we actually form bromine molecules. So we need 2 bromide ions, and they each lose 2 electrons. And if I go back, you will notice that the electrons for the cathode are on the left-hand side of the arrow. For the anode, they are on the right-hand side. So if I go back to my original diagram here, if I have got my negative cathode and then my positive anode, when the bromide is losing the electron, so here the bromide loses the electron, those electrons go on to the electrode and they then travel through the wires, through the bulb, and down to the cathode. And that's the electrons being pumped towards the cathode, which then allows the lead to gain electrons. So the source of the electrons in the cathode at first is just from the movement of the current, but then the source is actually the electrons that are being lost at the anode. So this is a way to allow the bromide to give its electrons to the lead without the electrons having to go through the molten solution, because they cannot travel in the molten solution. They can only travel through the wires and the electrodes. So the bromide loses the electron at the anode, it passes through the wires, goes to the cathode, and is then gained by the lead. And that is now forming my bromine molecules, which is my bromine gas, and my lead atoms. Both of my neutral substances being formed, and I can physically see them being formed during this molten process. Now, when we have our loss and our gain of electrons happening, we like to give them a specific name. So when we have a species that loses electrons, we call this oxidation. So if a substance loses electrons, like the bromide going to the bromine plus the 2 electrons, this is oxidation because the bromide has lost those electrons. Reduction is the opposite. Reduction is now when a species gains electrons. So if we have our lead 2 plus ions gaining those 2 electrons to form the lead atoms, this is reduction. And you can use the mnemonic oil rig to help you remember these terms. And you will see this a lot in lots of different textbooks and different revision materials. They all use the term oil rig, and it stands for oxidation is loss of electrons, reduction is gain. The most important thing that we have to understand about oxidation and reduction is that they always have to happen together. If one species loses electrons when it undergoes oxidation, the other species has to gain those electrons when it undergoes reduction. So when we combine these together, we call these a redox reaction. The RED coming from reduction, the OX coming from the oxidation. And this is something that you will go over in more detail when you do topic 2D, the reactivity series. But in terms of electrolysis, we should be able to write out the ionic half equation to show what is an oxidation reaction and what is a reduction reaction. And then in theory, we could combine them together to write the overall redox. Another thing that we need to note is that oxidation reactions will always happen at the anode, and reduction will always happen at the cathode. So you could use the mnemonic an oil rig cat to tell you that process. So anode, oxidation is loss of electrons, reduction is gain of electrons at the cathode. So now what we can do is we can look at different molten compounds and we can figure out what is happening here. So if we have Na positive and Cl minus for sodium chloride, our sodium is going to be attracted to the cathode because that is negatively charged. It is then going to gain an electron, and then it becomes a sodium atom. So we can then write out that this is a reduction reaction because we are gaining that electron, and we can write our half equation as Na plus 1 electron gives us, Na plus 1 electron gives us Na atoms. We can then do the opposite for the chloride. Well, the chloride is going to be attracted to the anode because the anode is positive. It is going to lose 1 electron, and it is then going to form a chlorine atom. Those are going to join together to form Cl2 molecules because Cl2 is diatomic. So we know that we are getting an oxidation reaction. And again, we can write out the half equation for that, and that is 2Cl minus, giving us a Cl2 molecule plus 2 electrons. And I could combine them if I wanted to, but we're not going to worry too much about the combination. If I did want to combine them, I have to make sure that my electrons cancel each other out. So if I have 2 on the right-hand side, I need 2 on the left. So I would multiply everything here by 2. And now those electrons cancel out with those, and I can write my overall redox reaction. I can do the same for aluminium oxide. So aluminium is Al3+, and my oxygen is O2-. My aluminium is going to be attracted to my cathode because that is my negative. It is going to gain 3 electrons to form the aluminium atoms. And we know that if we gain, then we are getting a reduction reaction. And then we can write out our half equation as we do here. So Al3+ plus 3 electrons gives us Al atoms. For our oxygen, the opposite, we're going to attract it to the anode because the anode is our positive electrode. These are going to lose 2 electrons to form oxygen atoms, but oxygen is diatomic, so we're going to form an O2 molecule, and we know that this is an oxidation reaction because we are losing electrons, and then we can write out our half equation as we have here. So 2 O2 negative ions will give you 1 molecule of O2 plus 2 electrons. And if I wanted to combine these, I need to make sure my electrons cancel out. So I need the same number on both sides. So I'm going to multiply the top by 3, which gives me 6 O2s, O2-, giving you 3 O2 plus 6 electrons. And I multiply the bottom by 2, giving you these coefficients. And then now my electrons are going to cancel each other out, and I get my overall redox reaction. The most important part for your exam is to make sure that you can write out the half equations. They don't put too much of a focus on the full redox equation. It's mostly the half equations in terms of an electrolysis question. The redox equation comes up more in questions that are to do with the reactivity series. Now we can move on to look at electrolysis of aqueous compounds. So in order to make an aqueous solution, we've taken an ionic compound and we have dissolved it in water. And that has then formed this aqueous substance. When we've electrolyzed sodium chloride solution, so this time NaCl aqueous, we see 2 gases being formed. Now this is different to the molten. If I go back to the molten, you can see that we formed sodium metal and a gas. But when we do the aqueous, we form 2 gases. And now we need to understand why that is the case. The difference here is that when we have an aqueous substance, we have introduced water into the mix. And water is a very weak electrolyte. So what that means is when the electricity passes through it, it can break down and form hydrogen ions and hydroxide ions. And we can show that in this equation here. So we have H2O liquid going to the H positive aqueous and OH minus aqueous. Now, rather than having just two ions, one being attracted to each electrode, we now have 4 ions, and we start to get some competition being formed. We have 2 positives being attracted to the negative electrode and 2 negative ions being attracted to the positive electrode, but only one of them can actually react. And what we have to be able to do as part of the triple course is to be able to predict which one. So if I have my aqueous sodium chloride, for example, I'm going to have my 4 ions being the Na plus and the Cl minus from the ionic substance, and then from the water I have my hydrogen and my hydroxide. And I need to determine from each of the 2 sets of the positives and the negatives which one is most likely to react. And there are certain rules that we use to do this. Now this is where knowing the reactivity series does come in very handy. So again, you may wish to look at the 2D video for reactivity series, or you can simply memorize the list at the moment. It doesn't matter whether you memorize it now or when you're doing electrolysis, or you memorize it when you do topic 2D, you are going to need to know it regardless. So when we look at the cathode, okay, so this is our negative electrode. So now we are focusing on the rules for the cations, which are, of course, our positive ions. We need to determine which one is going to react, and we use the reactivity series to tell us this. So if the metal is above hydrogen in the reactivity series, so if it is above that red line, then you are going to produce hydrogen gas at the cathode. So our example was sodium chloride. We can see sodium is very high on the reactivity series, much higher than hydrogen, so we are going to form hydrogen gas. If the metal is below hydrogen, you are going to form the metal at the cathode. So for example, if you're electrolyzing a copper, silver or gold compound, you are going to form copper, silver or gold at the cathode. So above hydrogen, you form the hydrogen gas. Below hydrogen, you form the metal. Looking at the anode is slightly different. It doesn't use the reactivity series. It uses just a very straightforward rule. If you have a solution of a halide ion, so a chloride, a bromide or an iodide, you are going to form the halogen at the anode. So you're going to have your Cl minus changing into chlorine. You would have your Br minus changing into Br2, or your I minus changing into I2. And of course, we use 2 of each of those ions. If you have anything else that is not a halide, so a sulfate, a nitrate, or a hydroxide, you will form oxygen at the anode. That is just the rule. You will either form a halogen or you will form oxygen. And we're going to look at this in our actual reaction to see why this is the case. So let's go back to our aqueous sodium chloride. So we have our NaCl. And at the cathode, when we set up our electrolysis apparatus, we turn the power on, and at the cathode, both the Na positive and the H positive ions are attracted. So we have both things going towards the cathode. Again, they are in competition. We need to figure out which one. So if I go back to my reactivity series, I can see that sodium is higher than the hydrogen. So Na is more reactive. So it is going to stay as an ion. The H plus is less reactive. So it is the one that is going to become the atom. So what happens is the hydrogen gains electrons. So it undergoes a reduction reaction to form hydrogen atoms, and these then combine to make H2 molecules, because of course hydrogen is a diatomic. So the sodium stays as an ion, the hydrogen gains an electron and forms a hydrogen atom, and they then combine to form your hydrogen molecules. So you could write out that you have 2H plus gaining 2 electrons to give you hydrogen gas. Now there is another way to look at this, and you would get credit for any of these two equations, is the fact that the hydrogen comes from the water. We can actually include the water as our half equation. So we are also then going to form some hydroxide ions, and we know that from the ionization. So the other way we could write this is we could write 2 waters plus those 2 electrons are going to give us our hydrogen gas plus our hydroxide ions. Both are perfectly acceptable in an examination. If they ask you to write the half equation to show the formation of hydrogen, you can either write it from the hydrogen ion after the water has already ionized, or you can write it straight from the water to form the hydrogen. And of course, that then forms the hydroxide. Both will be perfectly acceptable. Most people will default to this one, just because it's that little bit easier, but you would get marks regardless. Now we look at the anode. So again, we have our NaCl, and we have our power being turned on. We know that we get the electrons coming from the anode to the cathode, because we saw that in our molten. That doesn't change, and that forms the anode, causes the anode to become positive. So our positive anode attracts the chloride and the hydroxide ions. Both of these are going to be attracted, and we have to then figure out which one is going to react. And we've said that the chloride is the more reactive because it's the halide. That was our rule. If we have a halide, it's going to react. So the hydroxide stays as an ion, and our chloride loses an electron, which is our oxidation, and it then forms Cl atoms, and then these Cl atoms combine, because of course chlorine is diatomic, and we get a Cl2 molecule. And how do we write that? Well, we have our 2 chloride ions becoming a chlorine molecule plus 2 electrons. So that part has not changed from our molten sodium chloride. That was the same half equation that we've seen. The main difference that we see here is what happens at the cathode, because it's all to do with the reactivity. Now we need to think about the last thing, is the remaining solution. So if the electrolysis is carried on for a long time, we're going to see those products being formed. So our 4 ions that are in our solution are the Na plus and the Cl minus, the H plus and the OH minus. But we know that these 2 things are going to react. We've seen that the Cl is going to form the chlorine gas, and we've also seen that the hydrogen ions are going to form the hydrogen gas. So that now leaves us with Na and OH. So our sodium and our hydroxide ions are left over, and that then therefore means they are going to essentially form a solution, and it means that we form sodium hydroxide solution. So our remaining solution is alkaline, because we have that NaOH in that aqueous solution, because we've lost the hydrogen, we've lost the chloride to form the hydrogen gas and the chlorine gas, and what's left over is sodium hydroxide. So we have an alkaline substance, which we could test with universal indicator, and we would see a blue or a purple colour. And that just confirms that we make that substance. Another example is looking at copper sulfate. So we're going to shorten this slightly, but it's the same process that it goes through. So we need to think about what are the substances that react. Well, we have Cu2+ and SO4 2-, but we also have H positive and OH minus, because this is aqueous. So for the cathode, we're getting our copper plus our hydrogen, and copper is below hydrogen on the reactivity series. So we said if it's below hydrogen, we are going to form the metal. So we're going to get the copper gaining 2 electrons to make copper atoms. So we are seeing we're seeing a reduction reaction happening there. So we're gaining those electrons. At the anode, we've said that we're going to have the sulfate and the hydroxide. If we think back to our rule, the rule was if it's the halide, then we make the halogen. Anything else, we make oxygen. So SO4 2- is not a halide, so oxygen will form. And then how do we write that? Well, we have our OH minus is going to form, so we have 4 OHs forming water plus oxygen plus 4 electrons. And the best way for this is just to memorize that. But we know that we're going to have this OH. We have to form O2. We don't form hydrogen ions here. Instead, we form more water. So we form the H2O, and we then have to balance it out by saying that we have 4 electrons being formed. The remaining solution then left over is our hydrogen ions plus our sulfate ions, and this is a solution of H2SO4, which is sulfuric acid. And if we test that with universal indicator, we will see a red or an orange colour, because we know that that is acidic. I can then take that sulfuric acid that's formed, and I can actually electrolyse that. So if I have H2SO4, I'm going to have hydrogen plus the sulfate, and from the water, I still have hydrogen and I have the hydroxide. So at the cathode, we only have hydrogen ions. So that must mean that they're attracted, because we get the hydrogen from the acid and the hydrogen from the water, because this is still an aqueous substance. There is still some water in there. So we are forming the hydrogen ions, gaining an electron to form hydrogen atoms, but remember they are diatomic, so we must be forming our molecule. And at the anode, again, we have our same thing happening, that the fact that sulfate is not a halide, so oxygen forms, and we have that same process, our same half equation where we have 4 hydroxides giving us 2 waters plus the oxygen gas plus the 4 electrons. And what we see is that twice as much hydrogen is formed compared to the oxygen. And this can actually be an experiment to prove that water is is H2O. I could take the water and I could I could electrolyze it and form H2 and the O2, and I would make twice as much hydrogen as I do the oxygen. But I also see that with the dilute sulfuric acid. So just a reminder of how we predict these properties. If at the cathode the metal is high at the reactivity series, we produce the hydrogen. If it is low on the reactivity series, so it's below hydrogen, you're going to get the metal. At the anode, if you have a halide, you will make a halogen. And if you have any other common ions, so sulfates, nitrates, or hydroxides, you're going to make oxygen. These are must-know rules, because these are what you will use to predict the properties of an electrolysis reaction. So you have to know the rules and you have to know the reactivity series. So you might want to practice going over the reactivity series and making up a mnemonic or a rhyme to help you memorize it. And when we see different solutions, we are proving that this happens. So for example, if we have potassium iodide, potassium is high on the reactivity series, so we make hydrogen. And the iodide is a halide, so we make the halogen. Whereas for copper sulfate, which we just looked at, the copper is below hydrogen, so we make the copper metal. And the sulfate is not a halide, so we make the oxygen. So this table is just a summary of how we can put those rules into practice. And we've got our different half equations. So the key ones to remember are the hydrogen and the hydroxides. They're the ones that are a little bit more tricky for you to remember, specifically the hydroxide one. But if you can figure out what is being formed, then you can write the half equations and then eventually write the overall redox equation. So let's finish off by looking at some past paper questions. So sodium chloride solution is electrolyzed using a direct electric current. The ions in sodium chloride are Na+, Cl-, H+, and OH-. Which of these ions are going to be attracted to the cathode during the electrolysis? Well, we know that the cathode is our negative electrode. So we want to be thinking about the positive charges. So we have our Na and our H+, so our answer must be B, because both of the positive ions are going to be attracted to that negative electrode. For part 2, chlorine is one of the products of electrolysis. The half equation for the production is shown below, so we've got 2Cl- giving us Cl2 plus 2E, and we want to explain how the half equation shows that chloride ions are oxidized. And remember, we have our mnemonic, oil rig, and we've said that oxidation is loss of electrons. Well, the fact that the chloride has went from a negative charge to neutral means that the chloride is losing electrons to make the neutral Cl2. So the fact that we are losing electrons tells us that we are getting oxidation, and it's very important that we write chloride is losing the electrons. It's not chlorine. Chlorine is the halogen or the Cl2. Chloride is the ion. Please make sure that you get that the right way round, because if you say chlorine, you will lose a mark. Then suggest why the solution remaining at the end of the electrolysis is alkaline. Well, if we go back, we can see that we've got the sodium, the chloride, the hydrogen, and the hydroxide. So thinking at the cathode, sodium is high on the reactivity series, so we are going to form the hydrogen ions with our reaction to then make the hydrogen gas. We've already been told that chloride reacts to form the chlorine, so what is left over is the Na and the OH. So that means our remaining solution is sodium hydroxide because it contains Na plus ions and OH minus ions. And then for part 4, the electrolysis of sodium chloride solution does not produce metallic sodium. State what change you would make to the electrolyte to make the metallic sodium. Well, our aqueous is always going to make our hydrogen gas. So what we want to do is look at the other one, and we would have molten. So we want to use molten NaCl instead of aqueous NaCl. Because if we use the molten, then we only have the sodium and the chloride ions. We have no competition, and we're going to get our metallic sodium being formed. And then lastly, part 5, solid lead bromide cannot be electrolyzed. Molten lead bromide can. Explain how, when solid lead bromide is melted and electrolyzed, bromine forms at the anode. So this is essentially explain what happens at the anode during molten electrolysis. So in a solid, the ions are fixed in the lattice, so they cannot move. When it becomes molten, the lattice breaks, so the ions can move. That's the most important part. We have to understand that this only happens with molten because the ions can now move. Once the ions move, our Br- or our bromide ions are attracted to the anode because our anode is our positively charged electrode. When they get to the anode, the Br- lose electrons to form bromine atoms, and then we have 2 bromine atoms combining to form Br2, or bromine gas being formed. So we could even show our half equation. We can have our Br2- losing the electrons to have Br2 plus 2e. And that is for 3 marks. So you would have to have an explanation that links at least 3 of those points together. Okay, so we have our solid, they are fixed, and a molten, the lattice is broken so the ions can move. The ions are attracted to the anode, loss of electrons happens, and we form the bromine atoms, and they then combine to form the molecules. So there's the mark scheme for those questions if you have been trying them yourself. That is everything for topic 1I electrolysis. I would strongly recommend that you do make sure you know the reactivity series and you practice how to predict the products that are going to be formed. If you have any questions, feel free to leave a comment below, and we hope to see you back soon.